I think to introduce Xun, we have to first understand this little known fact that when video diffusion models work, when you generate those clips, they're actually happening from both ends. So that means when you're using VO or WAN or something, when we're waiting for that 10 minutes for the video to generate, the timeline has already been decided the moment you click the generate button. And then it starts to generate from both ends. But in June this year, I came across Shun's paper, and I got really excited because he's figured out a way to be able to generate videos auto-aggressively, so frame by frame, in a similar way that LLMs kind of predict the next token. He figured out how to predict the next frame, and that's really exciting. So this paper is called self-forcing, and most of the real-time video AI models that have come out in the last 4 or 5 months have borrowed ideas from his paper. So I'm really excited to have Xun on stage and share with us a little bit about his vision of where things go from here.
Yeah, thank you so much for the introduction. So today I'm going to talk about video world models, about my recent research, how they push towards a better, a new paradigm of video models. So video models have been used a lot for content creation purpose, basically Sora 2, Veo 3, or Clean. They are using video generation models to create those either films or short form videos. But basically, most of them, they only allow users to passively watch the video. So once the video is generated, they are kind of fixed, and users have no way to actually interact with it. So my goal is to how can we go from video generation models to video world models. So I will first explain why the existing paradigm is not able to do the so-called world model. So most video generation models, they rely on the diffusion model. So basically, the input is really text with some random Gaussian noise, and they go through a diffusion transformer with full or bidirectional attention. So each token can attend to every other token. And basically, there's iterative denoising process, and after a long wait, the video is generated, and after it's generated, it's not changeable. So the users can basically watch the video. It's perfect fit for mass media, where the video is created once by content creators and distributed to many consumers. But it's not really suitable for interactive applications where the information flow should be bidirectional, that the user also wants to influence how the future of the video. So there's another very hot topic, world model. I guess that's also everyone here is interested in. So what does that mean? How do you differentiate video generation models with world models, right? So so my personal definition is the so-called world model Turing test. So ultimately, a world model is perfect if living in a world model is visually indistinguishable from living in the real world. I use the word visually because it's a video model after all. It generates pixels. It's not able to fool your brain to in the Matrix simulator to make you feel you had a lunch, but you actually hadn't. So ideally, you wear a VR headset, and everything is generated by video world model, and by watching the pixels, the visual signals alone, you cannot really distinguish whether you are in the real world or in the virtual world, like a Matrix, but just visually. So what are we lacking, right? So what do we need to go from the existing video generator to a world model? So I would say there are a few important things that we need to improve. First, the video models are not causal. So by not causal, I mean our time is unidirectional. The past affects the future, but the future doesn't depend on. The future doesn't affect past. That's not how normal bidirectional attention diffusion transformer works. Because for diffusion transformer, every token can attend to each other. So that's not how our real world works. And if you apply this thing in the real world, and there's some real-time controllable signals, basically you will need to, for the user to specify all the entire features, so then you can start generating something fast, but that's already a long time ago, so it kind of like constrain the latency in like interactive applications. So that's kind of like related to the second disadvantage of the existing video generation pipeline, that they are not interactive, like they cannot respond to user actions in real time. Like if I'm interacting with the real world, like I can use my hand to like kind of like move objects, right? So, but if I mean, like VR headset, I raise my hand, I say I cannot really interact with anything. I know it's not the real world, right? So interaction is like definitely an integral part of a world model. It's very necessary. And another issue is like the existing video generators, they are not like persistent. So they can only able to generate like a very short video clips, like 5 second, 10 second. But you cannot like generate a minute long or like hours long video with like perfect long-term consistency, unlike the real world. So, and finally, another important advantage is like just like not fast enough, right? So they are like not really real-time responsive. So like generating a 5-second video may need like several minutes in most standard diffusion model approach. So we have been working on like to push this new paradigm of like autoregressive diffusion transformer with causal attention. So it can be like a better fit for the video world model. So basically, instead of like generating the entire video with bidirectional attention, we do like frame-by-frame generation. Like temporal dimension is autoregressive generation. So at each time, we just generate a single frame or chunks of frames, and basically user saw this frame and it can like perform some actions, right? So, and when it injects some actions to the model will like almost instantly respond to it to generate the next one, and conditioned on the previous history and a new noise. And another advantage of this autoregressive formulation is like it's very easy to like extrapolate, like to generate like very long videos. So for like bidirectional diffusion, you're just like kind of fixed length. But for autoregressive models, it's not like a really like hard constraint. It's much easier to generate a longer video. So this is more suited for like the interactive experience where the users like see some input frame, they perform some actions, and the world model or real-time video model respond instantly to it. So the first work we push towards this direction is like in COSVID. So basically, given a pre-trained video diffusion model, like trained on internet video datasets, with like full bidirectional attention, we can use the weights. We found that we can use the weight, initialize the model with the weights from the pre-trained bidirectional diffusion transformer, but just change the attention mask. So basically, we enforce some mask constraints in the attention computation so that each token can only attend to tokens in the same frame or like tokens in previous frame. So basically, here like it obeys this temporal causality constraint, like only past can affect future, but future cannot affect past. And also, it enables like the use of KV caching during inference to accelerate the computation. So if you don't use KV cache, like if you basically for generating each frame, it will like take the entire history and perform like attention, and all the KV needs to be kind of like recomputed. But similar to like LLMs, like when you have this causal attention mask, you can do like KV caching, so you don't have to like recompute the caching from the historical frames, which greatly accelerate the computation, of course. And another important thing is like we use diffusion forcing, which basically like for normal diffusion models, right? For the left-hand side, you have like the same noise level for all the frames. But at inference time, like for example, for autoregressive inference, usually like your historical frame are like entirely clean, but your current frame is like has some noise, right? So this like training scenario would like not generalize very well to this inference scenario. So basically, diffusion forcing is like a prior work that during training you just like give like independent noise levels to all the input frames. So it can basically cover all the possible scenarios. So it can generalize better at inference time. And another thing, to accelerate the inference, we use distribution matching distillation, or DMD. So like normal diffusion models need like 50 steps or like 100, even 100 steps to really like generate very good results. But with like time-step distillation methods like DMD, you can like generate pretty much same quality results in like just 4 steps. So basically, you give this, yeah, maybe like I will show the full picture. So you have a data set of video, and you just like random sample some video from the data set, and you use diffusion forcing to inject like frame independent level of noise. And then you have a causal diffusion generator that has like this causal attention mask, where like each row is kind of like a query frame, and it only attends to all the tokens in the same or previous frames. And you give this generated video to a teacher model, which is also initialized from the pre-trained video diffusion model. And the teacher model does not have like causality constraint. It can have like bidirectional attention. So basically, that's like the DMD algorithm to distill this causal student into a few-step model. So show some results at that time. It's a year ago, but at the time, like the video model-based model quality is very good, and we can kind of like generate this kind of video in a very efficient manner, almost real time. So this work was done like internally at Adobe, and the results was like using an Adobe internal model. But when we tried this like on some open source model, like smaller model like 1, 2.1, we observed like worse results. So for example, like in some cases, you can see like the color becomes increasingly saturated over time. And also, like in some cases, you can see some flickering, for example, near the coral, like between the different chunks of generation. So it took us a while to like identify what's causing those quality degradation. So we found that the root cause is like still just like a train test distribution mismatch. So basically, you are training your model to on one distribution, but you are testing your model with another. So in the diffusion forcing training paradigm, basically when you generate one frame, it's conditioned on context that's like noisy, right? So and also like they are like ground truth frames. So you take a ground truth video from your data set and you use it as the input. So all the previous frames, they are like perfect ground truth video from your data set. But at inference time, actually, you are asking the model to do a completely different thing. So at inference time, basically, you generate one frame at a time, and when you generate the current frame, all the previous frames are generated by the model itself, and also like all the previous frames are completely clean. So it causes a distribution mismatch, and basically, the training objective of DMD basically tells the model to generate something that's in the real video distribution, but because the thing that model generates during training is not the same thing that the model would generate during inference time, the training objective is not really like pushing the model to do the right thing. So basically in self-forcing, we kind of solve this problem by aligning this inference and training behavior. So basically, we just let the model to do inference during training. So at inference time, we have this temporal dimensional autoregressive rollout with KV caching. And for spatial dimension, we do like iterative denoising. So basically, we generate a video frame by frame, and for each frame, we do like a diffusion, iterative diffusion process. So specifically, like here, for example, for the first frame, it goes from like pure noise to a frame. Actually, it goes like it went through like several iterative denoising process, but I just want to show one here. And for the next frame, it takes the clean first generated frame and another random noise. It generates the second frame, and it repeats this process again to generate the third frame. So this process is like how the model in Causeway was used during inference time, but it was not how it was used during training. So here we also use this process actually during training. And this is kind of like the KV cache, the attention mask illustration. So when you finish the computation of the first frame, you get this clean first frame, and you re-encode this clean first frame to generate the KV cache of it. And so when you generate the later frames, you only need to attend to those KV cache without needing to regenerate them. And so here's a demo. So basically, we have the first time to like really show like a real-time video generation results with very good quality. So here, basically, users can click like start generation, and it will just play immediately with like less than a second latency. And this is done like on one H100 GPU. So like in Causeway, we tried DMD, but basically it's kind of like more general method. So you can like apply any other like distribution matching loss. Basically, you want to make sure the generated image distribution is like similar to the real video distribution. So you can also like use methods like GAN, and basically we show like very much better results compared with like Causeway under the same setting. Like you don't have like oversaturation, you don't have like some flickering. I think there's some video compression effect, but and the motion is actually much more natural. Also, like the results are actually very slightly better than the teacher model, but we observe like a much lower latency, like from almost 2 minutes to just like less than a second latency reduction, and a lot of like we achieve like we can generate videos in like 70 FPS, and the quality is like really great, like comparable with the teacher model. And also like the training is like quite efficient. Like people may expect like because you have to do like this sequential rollout, it may not be like super efficient, but on modern GPUs. But actually, because at each time we still like processing a chunk of frames, and each frame has like a large number of tokens. So we observe like it's not a really like bottleneck factor for the training, and the training is like still efficient. Like we can achieve like better quality than alternative strategies, alternative like parallelizable strategies under the same workload training compute budget. So yeah, self-hosting is great, but we still have some limitations. Like we observe like some error accumulation when you generate a longer video than what the model is trained on. So when the model is trained on like just 5-second video, but you want to like use it for like 30 seconds, actually you will like gradually see like the color becomes also like oversaturating over time. And also like self-hosting is just like text to video, and it's not really like yet support interactive control. So in a follow-up work, we kind of like resolve these two limitations. So this is a new paper called motion stream. So here, like we can generate a very long video, and also like with interactive control from user. I will play the demo. So user basically can use the mouse to control the motion of the video. Like here, you see this green box, and you can kind of like control the waves in real time. It's a real-time recording or on a single GPU. And similarly, like users can fix like this red dots will tell the model, okay, I want this pixels to kind of stay there, and I just want to move the head, and basically, yeah, the head will kind of follow the direction of the the mouse, and okay, now I just wanted to raise the left hand. We'll keep other thing fixed. And then maybe I want to raise the other hand as well. And you can see that like this video is pretty long, actually almost a minute, and we do not observe like the previous error accumulation in the self-parsing example. So here, like I'll talk like two aspects, like one how we add interactions, and another how we resolve this error accumulation issue. Basically, we add interaction by conditioning the model on motion tracks. So basically, for like the training video, we kind of annotate this dense motion tracks telling the model like how the points like in the same position are like moved across different frames. There are like existing point track methods that can kind of like get the motion from the any ground truth input video, and we're doing training which kind of like randomly sample sparse amount of tracks. And we use the track to kind of like condition a diffusion model. So we encode the tracks to get like track embeddings and use like something similar to like control net to condition the bidirectional video diffusion model, so we can use it as a teacher model. And then basically we use something similar to self-forcing to distill into a few step student, but we do some additional observations. We do have some additional observations that basically we found that no matter whether the diffusion model is like bidirectional or it's like causal, there's like a lot of heads that where the model only pays most of the attention to the initial frame. Like for example, for the bidirectional model, we saw like some heads that are only paying attention to the initial frame. Also for the causal model, there's like similar heads. And also like most of the time, the attention is pretty concentrated in the local like diagonal window. So basically, the lighter the color is, the heavier the attention is. So you can usually like see this kind of diagonal attention patterns. This kind of motivates us to have like a sparser attention and attention sink to both reduce the computation cost and to kind of anchor the model so it can always attend to the same initial frames, so it can reduce the error accumulation when you extrapolate longer during what the model is trained on. So, and then basically we do like this self-forcing style rollout, but with like different attention sink and the local attention window. So you still do like this autoregressive generation during training, but at each iteration you maybe like randomly select one attention mask, and that attention mask kind of like dictates how you would use the attention during training. Like for example, if you select the middle attention mask, it will like always attend to the first frame and also the previous frame when you generate the current frame. And yeah, so that's basically how it works. And I show some demo later, but still this kind of method has some inherent limitations. So you can generate a very long video, but because it only uses like kind of local attention, so it wouldn't really like remember things that happened a long time ago. For example, if you do this kind of sync plus local attention, most of the context that's not either of them will be kind of forgotten by the model. It's okay for some use cases like interactive motion control or like video-to-video translation, but for some word simulation case, you really want the model to remember every details it has seen. So one can also use like full attention, but the problem is like its attention is quadratic, and even with KV caching, it will be linear. To generate like each frame, the computation cost will grow. So basically, the model will become slower all the time, and you don't want to play a game rendered by a water model, but it becomes increasingly laggy over time. So basically, there are like really like two hard constraints for word simulation. First, you want the model to have like long-term memory, and also like you cannot sacrifice your latency. So your model should have like a constant FPS, constant generation speed, no matter how long the model has seen. So there's like one type of architecture that's really suited for this purpose, both long-term memory and constant generation speed. So it's state-space models, or like Mamba is one of the famous variant. So in this paper, we tried like to use state-space models for video world modeling. So to give the model long-term memory capabilities without sacrificing latency. And one particular thing is like instead of usually like Mamba would do like for video it would do kind of like zigzag scanning, so it will like scan one frame from top left to bottom right in like the raster order scan. But we found that that's like standard strategy is not like super effective. So basically you have a limited memory size, and also like with that scan order, like you would like finish scanning one frame, and then you see the same token in the same location in the next frame, but you already basically two tokens that's at the same location, but in nearby frames, they are like really far apart from each other in this scanning order. So the model basically spends most of the capacity in like modeling spatial interactions, but doesn't really like do much in like temporal memory. So we propose this kind of new types of scanning algorithm. So instead of like scanning one frame and then scan next, we scan like a very small block, maybe just one location for one frame. And we have like this kind of like parallel Mamba scanning head. So in this example, we like divide this video chunk into like 4 blocks. So for each head, like we scan like one block spatially and then go to the next location. So temporally adjacent tokens are much closer in the scanning, so the model can like remember things that's like much longer temporally before. And we kind of complement it with like local attention, similar to the previous work, to better model spatial interactions. And for example, like we show like in some toy tasks, like if you in this memory maze, if you go one direction for some time and then you go back, with the state-space models, actually you can kind of get the exact same memory, but for like causal transformers with like limited attention window, it will forgot what this is before. And yeah, there are some like metrics that we show, like the if you do like full attention, of course, you remember things pretty well, but it's also like very slow. If you do this kind of causal attention, then you can, local attention, then you can remember things in the local sliding window, but you kind of forgot about like everything before. After it's like longer than the attention window size, your memory quickly drops. But if you do like our method, you get like a decent long-term memory without really like sacrificing any latency. And we use it to like generate 3D consistent Minecraft words. Cool, yeah, so a summary of the talk. So I initially talked about like 4 problems that kind of preventing those existing video generative models to become like true interactive world models. Each of our work kind of like solves one of the problem mentioned. So for the causality in CausaVid, we explore like how can we convert pre-trained diffusion models with bidirectional full non-causal attention into like a causal attention generator. And in self-forcing, we explore like how can we achieve real-time generation without really like sacrificing quality by aligning this trend test distribution mismatch. And for the interactiveness in motion stream, we explore like how can you use motion control signals. For example, something like users can input with like mouse controls to interactively guide the generation. And for the persistency issue, we explore like how can you use state space models to enable the model to really have long-term memory for word simulation tasks. And all of this work would not be possible with the wonderful collaborators, and I want to yeah, also thank you for listening, and also thank them for the contributions. Yes.